Hiya Tim. If you struggle with these, it's worth me pointing out that, as ever, I did choose the most difficult questions that you can get on this. So on my software that I've got where I can choose exam questions, I can choose the different levels of question, and I never give you the easiest ones. I always choose the harder ones. So because obviously if you can do the harder ones, generally you can do the much easier questions. So let's start. I've got a boat floating on the sea, and I've got a free body diagram for the boat. So a free body diagram is the forces acting on the boat. I've got the weight in this direction, and it says to complete that free body diagram. So the crucial thing here is that I make sure it says here the boat's stationary, it's not going anywhere, so therefore I need to make sure, so that's about 4.9 on my diagram. So when they mark these, it always says on the mark scheme by eye that they look equal and opposite. So they don't get out a ruler and measure it, they just glance at it and see if it looks the same length by eye. So, and for the second mark, I need to label that as upthrust. It then says to calculate the mass of the boat using the information I've been given. So the gravitational field strength is 9.8. So the first thing I need to do is, if 1 centimetre is 5 kilonewtons, I need to measure that, and I make it 4.8 centimetres long. So if it's 4.8 centimetres long and each centimetre is 5 kilonewtons, then in total it is 24 kilonewtons, and therefore I have my first mark. If force is mass times acceleration, then the force, I need to change that from kilonewtons into newtons. 24,000 newtons is the mass times the acceleration is given to me here as 9.8. So therefore I have a second mark. So if I rearrange that equation and calculate 24,000 divided by 9.8, it's 2449. Now you'll have slightly different numbers to me just because of this measurement here, but if just as long as you've followed the same method, you're getting all the same marks. They will give a lot of tolerance within this. So I've got 2449, but crucially the thing that everybody misses in these questions is they've asked for it to 2 significant figures. They do say in bold, give you answer to 2 significant figures. You need to really look out for that. So if it's 2 significant figures, in this case mine is 2,400, and that is my fourth mark. Oh, I forgot to give myself a third mark, didn't I? And my fourth mark is from turning it into 2 significant figures. Here you could have a real wide range of answers, because once you've rounded it to 2 significant figures, that's huge, isn't it? So you could get all, you know, up to 2,600. So don't worry if yours is significantly different to mine. When the boat propeller pushes the water backwards, the boat moves forward. This is Newton's third law. I've got 2 things interacting, causing equal and opposite forces. 64% of people got that right in this exam, which actually is quite startling. It's a pretty basic example of Newton's third law, and only half of the students got that right. So I've got a boat towing a dinghy this time. The tension force is caused by a horizontal force, and a vertical force. So I've got my tension force here, and I can resolve it into 2 components. I'm given the 2 components of the force, and I've got to draw a vector diagram to measure the magnitude and direction of the tension force. Oh, I thought I was going to be given a grid to do it on, sorry. Okay, so if I decide to make each 1 centimetre be 50, I probably should do 2 centimetres, but anyway, yeah, I should probably do 2 centimetres, but anyway, life's too short. So that's now 150. I then have 50 up like so, and then I can measure the tension force here. Hang on a minute. That's because I didn't turn over onto the right page. I do have a grid. I thought I did. Okay, so if I make it bigger, sorry, I'll get a much better answer, won't I, if I make it bigger. So I'm using 2 squares to be 50. I'm using 2 squares to be 50. I can then measure the resultant force. Note I put arrows on the end of my forces. Always want arrows on the end. So the resultant force going in that direction there. I can measure that and we'll all get slightly different measurements. I'm getting I'm getting 11.7 centimetres. So 2 squares, 3.7 centimetres was 50. So how many lots of 50 have I got? I've got 3.1 lots of 50, which is 155 newtons. Again, we're all going to have got quite different readings for that, particularly because if you've printed it out. If you're measuring off the screen at home, if you were trying to do off the screen measurements, or if you've made your own free diagram on line paper, you know, we're all going to have done it differently. So we're all going to get slightly different values for it. The direction of the force I've shown using the arrow here, and all I need now to do is make sure that I've given it an actual reading, which is 18 degrees from the horizontal. 9% of students got that question right. So it's really quite a small percentage of students who are able to do these sorts of diagrams. Figure 1 shows an aircraft flying at a constant velocity and constant height above the ground. So it's got balanced forces acting on it. Complete a free body diagram to show the other 2 forces acting on the aircraft. So I'm doing a free body diagram on an aircraft. So I need it to, by eye, look like I've got equal and opposite forces to show that I understand. So it's about 3.7. I always get a ruler out, even though I know that they're going to just do it by eye, because I just think that in the nervous moment of an exam, I'd just rather be sure that they're going to give me the marks. So therefore I have got the thrust of the aircraft's engines, and I have got the weight of the aircraft. So, a small aircraft accelerated down the runway, 4 meters per second. It started from rest, speed went up to 34, so I've got a change in velocity and acceleration. I'm calculating distance, so therefore I need v squared minus u squared equals 2as. I haven't got time, so I can't, and then calculating distance, so this has got to be the one I'm using. So I've got the final velocity squared, take away the initial velocity squared, is 2 times 4 times the distance travelled. The thing that people do quite a lot now is they lose the squared sign. I don't know why, but it's quite often the case that they forget to square the 34. Yeah, no idea where that comes from. So therefore 1556 is 8 times s. So therefore 1556 divided by 8 equals 144.5. And then what do I look for? What significant figures am I going to? I'm going to 2 significant figures, which is 140. So what we need to do next then is I have an aeroplane being towed by a glider. The tension force in the cable can result into a horizontal and a vertical component. The tension in the cable is 2000 newtons, angle 20 degrees. I'm drawing a vector diagram. So, not left me much space, and it's obviously just the way it's printed, hasn't it? I'm going to do my horizontal line across the bottom there and measure my 20-degree angle. And I'm going to decide to do 1 centimetre as 500 newtons. So I'm going to do a 4 centimetre line to be the 2000 newtons. So 1 centimetre here is 500 newtons. I'm then going to use my protractor to accurately get the down. There we go, and there is the vertical force. I'll put an arrow on for the horizontal force, an arrow on for the tension, and then I can start my measuring. I've got 3.8 centimetres times 500. Which is 1,900 newtons, and in this direction I've got 1.6 centimetres, which if I times that by 500 is 800 newtons. Again, we're going to all get quite different answers from that, because it always is the case when you start trying to calculate things like that, do drawings like that. So once you've done that, it's actually got two little lines for you to write your answers onto. Next question. When two objects interact, they exert forces onto each other. So I've got two interacting objects, therefore they are equal and opposite forces. I have a fisherman pulling a boat. The force acting on the boat are these here. They're acting on the boat. This isn't Newton's third law. These are not equal and opposite forces. These are forces acting on the boat. This is Newton's first law. So the fisherman exerts 300 Newton, resistance of 250. So what will the motion be? It will accelerate. You can't just say it's going to move. You have to say it accelerates. If you've got unbalanced forces, you've got acceleration. So it'll accelerate, and it'll accelerate forward or to the right. You can say either. When the boat reaches land, the resistive force increases to 30 newtons. Balanced forces, but it's moving. So, therefore, what will the motion of the boat be now? Well, like I said, I've got balanced forces, but it was moving, so it will then continue to move at a constant velocity. Why? Because I've got balanced forces, or I could say zero resultant force. So it will continue to move at the same speed and in the same direction. Then another fisherman comes to pull the boat with a force of 300 newtons, and I'm instantly seeing what this is. It's a parallelogram of forces, isn't it? They're going to ask me what the resultant force is, surely. Add to diagram 2 to show a single force. Yeah, resultant force. So if I was in an exam, I would measure this much more carefully. I would measure that angle and then measure the angle over here. I'm just going to do it by eye here for you, because I don't want you hanging around watching me do a whole lot of angle measuring. So if I just show you that that is what you would end up constructing, so that then you could measure the diagonal here, which is the resultant force. And if I measure that, so drawing that parallelogram is 3 marks. Measuring that line there is another mark. And then I'll accept anything between 545 and 595 newtons. So you're going to measure that, work out what the scale is, multiply by to get that force there. So these parallelograms should be starting to feel a little bit more familiar, I'm hoping, to you by now. Diagram showing a boat pulling a water skier. I've lost page 7. Should have had this set in order when I started. Okay, so arrow represents the force of water produced by the engine. What force causes the boat to move? Typical Newton's third law question, this. Very, very few students got any marks for this question. Negligible students. It's because this causes an equal force from the water on the boat, and it's in the opposite direction, or forwards direction, you could say. Now, crucially, I hope you can recognise that you wouldn't get 2 marks for just there'll be an equal and opposite force, because the crucial thing they're trying to see is that you understand the force is on the boat and it's from the water, and it's in an equal amount and in an opposite direction. So that bit of extra information is really crucial to getting that mark. The boat accelerates at a constant rate in a straight line. This causes the water skiers' velocity to change from 4 to 16 in 8 seconds. Calculate acceleration. This is always well answered generally. I've got a change in velocity over time here, haven't I? So my change in velocity from 4 to 16 over the time of 8 is 1.5 meters per second squared. So you get 2 marks for the 1.5 and 1 mark for meters per second squared. Mass of 68 kilograms, resultant force, so force is mass times acceleration, so therefore I have a mass of 68 times an acceleration of 1.5, which is oh god blimey, 102. Oh, I'm doing this too long now. Draw a ring around the correct answer. The force pulling the water skier forward, so be careful. So the force pulling the water skier forward, how is that different to part 2b? So what's this? The force acting on the water skier when he's accelerating. So he's accelerating, and the force acting on him compared to the force from the boat pulling the water. They're both forces on the water skier. They're not equal and opposite forces. They're both acting on the water skier, and he's accelerating forward. So therefore, it must be greater so that it can overcome the resistive force or the friction of the water. Not many people can name that force. There weren't many people managed to name resistive force or friction. Some people called it water resistance, or yes, there were some quite bizarre names. If in doubt, call it friction. So be careful with your naming of that force, I would say. Some people call it upthrust, apparently. Water resistance would probably get it in this case, actually, wouldn't it? Okay, a brick. So, okay, question 5. So, brick is pushed, but it's not moving. I've got all the forces labelled on my diagram. The pushing force doesn't make it move. Why? They're simply looking at Newton's first law, aren't they? Because it is balanced by the friction force. So you could say it's equal to the friction force, would get that mark as well. The weight doesn't make it move downwards because it's balanced by, or is equal to, the upwards force of the table. A bigger pushing force does make it slide. What will that do to the surface of the table? Well, the obvious answer there, will heat it up. You could also just say it damage it or wear it away. That would equally get you the mark. Question 6. I have a cargo ship. This was a really badly answered question. Very few students could answer it. And again, it's because it's based on Newton's third law, and very few students really get it. So water exerts a force on the ship. Which direction does it act? So the weight of the ship, that's down, and water exerts a force up on the ship. So how does the force exerted by the water on the ship change as the ship's loaded? As the ship's loaded, increases the weight, so therefore it will increase the force, the upward force on the ship, because they're equal and opposite forces. Why has that force changed? Because the ship is heavier. quite simply, or because more water has been displaced is an acceptable answer. So if you get Newton's third law, then that is quite a straightforward question, I would say. But like I say, extremely badly answered. Very few students got the mark. For the forces acting on a container ship shown. This question was a bit more straightforward, a bit more Newton's first law, isn't it, this? So ship moves forward when B and D are unbalanced, but if B and D are balanced, then it will get to a steady speed. If all the containers are taken off, then force A will change, or I could say force C would change as well. That would get me the marks too, because of Newton's third law. Final question. Apple floating on water, apple's not moving, so there can't be any forces acting on it. Do you agree? So this is a test of Newton's first law, and no, this again was very poorly answered. No, it's not true. I don't get any marks for saying no, but I get marks for saying because gravity or the weight of the apple is acting down, up thrust from the water is acting up, and these are balanced forces. I'm always surprised that they don't insist on you saying that the forces on the apple are balanced. But anyway, they don't. They're quite happy just to say it's balanced forces there. So that's the end of this, and next week we'll do a little bit more work on using calculations in exam questions. It's pretty straightforward. I think you won't find it too challenging once you start having a look at it. It tends to be fairly obvious which equation you're going to choose to use, and hopefully after doing those questions you're feeling a bit more confident about answering questions on Newton's laws.